Hello. Here we are as promised, working through some examples from 15.8 where we are using spherical coordinates in order to take care of some integration. So in this particular problem, we are asked to evaluate a triple integral of x squared plus y squared dv, where E is the solid above the xy plane and below the sphere x squared plus y squared plus z squared is equal to 1. So what they've just described here, if we were to, draw the XY plane, something like this, they've just described trying to draw this is a whole nother thing, a sphere on here, something like this. You could think of our XYZ octant being drawn on there, but I'm emphasizing the XY plane on there so that you really see that this really is just the upper hemisphere, nothing below it, only the stuff above the XY plane. And so we have to figure out what would the bounds of rho, theta, and phi be in order for us to get the upper unit hemisphere. Well, because it is a unit hemisphere, that tells me that rho is going between 0 and 1. Because it is the full hemisphere going all the way around the z-axis, that tells me that theta is going between 0 and 2 pi. Now, because it's just the upper half of the sphere, so the upper hemisphere, that tells me that phi, remember phi makes a positive angle, it makes a positive angle with the positive z-axis. So I have to imagine starting on the z-axis and sweeping down to the y-axis, that's a whole pi over 2 radians. So phi goes from 0 up to pi over 2. All right, so that takes care of my bounds. That really wasn't bad. Now we need to deal with the integrand. And I want to show you how to handle the integrand most easily when it's just x squared plus y squared. So in a previous example, I was highlighting to you all how x squared plus y squared is just, it's actually rho squared, but without the z squared, because remember that rho squared is equal to x squared plus y squared plus z squared. So if you only have x squared and y squared, then that's equal to rho squared without, so minus, the z squared. And the reason we do that is to avoid having to use all of the cumbersome conversions for x and y into spherical. If we can go straight to rho squared minus z squared, things are a lot easier because z is just rho cosine phi. So I can rewrite this as rho squared minus, and I have rho cosine phi, I'm going to square it. So it's rho squared cosine squared of phi. And now I'm already in my spherical coordinates, and I don't have the mess of what x and y would be. So try to use this as you're going through if it ever comes up. So that takes care of my integrand, my differential. Now if we're going from rectangular to spherical, we have to remember that there's like this conversion factor that shows up in our differential. We get a rho squared, we get a sine of phi. That's the extra. And then we have d rho, d theta, d phi, or whatever order we want to go in. Okay, looks like we can go ahead and set this up. So the triple integral over E of x squared plus y squared dv will be written as a triple integral, I'll put in my bounds next, of rho squared minus rho squared cosine squared of phi times dv, which is rho squared cosine of phi, and then I suppose we can just go ahead and go with the order, d rho, d theta, d phi. Then that means my inner integral is for rho, so it's 0 to 1. Middle is for theta, 0 to 2 pi. Outer is for phi, 0 to pi halves. Okay, now what I need to, I'm so sorry. I accidentally wrote a cosine in my differential, and I really meant a sine. Okay, that would have been disastrous working through. Okay, so now What I want to notice is that in total, I have rho to the fourth, and I'm going to factor that out of everything. So this is equal to the integral from 0 to pi halves, the integral 0 to 2 pi, the integral 0 to 1 of rho to the fourth times, and I'm going to distribute that sign in here. We have sine of phi minus cosine squared of phi times sine of phi. So all I'm doing right here is just rearranging all this multiplication so that it's easier for me to see my distinct functions when I'm integrating. So d rho, d theta, d phi. All right, now we can focus on the inner integral first, and then we will handle the middle one. And finally, we will handle the outer one. So the inner one, A, we're dealing with rho, integral from 0 to 1 of rho to the fourth times this sine of phi minus cosine squared of phi, sine of phi, d rho. Well, the sine and cosine stuff is just a constant, so I'm really focused on rho to the fourth, which gives me 1/5 rho to the fifth times the sine of phi minus cosine squared of phi, sine of phi, going from 0 to 1. When I evaluate this from 0 to 1, the contribution from 0 is nothing, and the contribution from 1 is just a fifth. So this just becomes 1/5 sine of phi minus cosine squared of phi, sine of phi. All right, this is my integrand for B. So I can go ahead and work on B. B is dealing with theta, so we're going from 0 to 2 pi of 1/5 times sine of phi minus cosine squared of phi, sine of phi, d theta. Well, everything's a constant in here, so I'm just going to get theta times this ugly constant, and I'll evaluate theta from 0 to 2 pi. So we get a theta over 5 times sine of phi minus cosine squared of phi, sine of phi, from 0 to 2 pi. And that just gives us a 2 pi over the 5. So I have 2 pi over 5 times sine of phi minus cosine squared of theta, sine of phi. All right, this is my integrand for C. All right, and for C, what we're going to get is the integral, if I remember, 0 to pi halves, and this is for phi. Honestly, we can write that 2 pi over 5 on the outside just so that it's not an eyesore inside. Okay, so we're dealing with sine of phi minus cosine squared of phi, sine of phi, d phi. Okay, for the first one, it's a direct integration. The antiderivative of sine is minus cosine. For the second one, that's a u sub. So the u sub does not apply to the whole problem. It just applies to that second part. So my u sub, actually I'll do it over here. My u sub, u will be equal to cosine of phi, and du will be minus sine of phi d phi. So I was going to take care of that negative sign as well. It looks like we'll be handling just u squared du, which is 1/3 u cubed. Well, that's great. Okay, so we have our 2 pi over 5 still hanging out. Antiderivative of sine of phi is minus cosine of phi. And then we found the antiderivative of the second part will be a plus 1/3 cosine cubed of phi. This is going from 0 to pi halves. All right, at pi halves, we get 0 contribution because cosine of pi halves is 0. And so we have 2 pi over 5 times negative 0 plus 0. That's evaluating at pi halves. Minus, in parentheses, a negative cosine of 0 plus a 1/3 cosine cubed of 0. Simplifying this, I still have my 2 pi over 5. And now inside here, this becomes a negative 1 plus 1/3, which is a negative 2/3, times a negative on the outside gives me a positive 2/3, for a grand total of 4 pi over 15. Okay. So that took us through quite a bit. In this problem, interestingly enough, integrating would have, in x and y, would have been a bit painful just because of the bounds on a sphere. But the bounds that we used in spherical coordinates made that part super simple. We had a bit more work on the integration part, but it wasn't too bad. Okay, next example. Find the volume of the solid that lies within the sphere, x squared plus y squared plus z squared is 4, above the xy plane, and below the cone, z equals the square root of x squared plus y squared, using a triple integral. So what we have to remember here is that the volume is equal to the triple integral over e of 1 dv. Okay, so our integrand is 1. We've got to work on the bounds. All right, so again, we are above the xy plane, and we are below a cone and inside of a sphere. Oh, goodness gracious. Let's see what this looks like. So here is the top half of a sphere. I'm only doing the top half because we're told that the xy plane is one of the bounds. Okay, now in this sphere, there's also a cone. In the cone, it's the standard cone. Z equals square root of x squared plus y squared. If we can remember, its phi is equal to pi fourths. So that bisects here. Bisects, get that a little bit better. Bisects here, and then we can go ahead and get our cone. Now remember that a cone actually goes on forever. Okay, so let's draw this beyond the sphere so we can kind of really see what's going on here. It's kind of a weird cutout shape. All right, they're telling us that the volume we want to calculate is within the sphere and below the cone. So what they want is this region right here. Not inside the cone, but below the cone. Okay, we need to remember that the standard cone is, well, first of all, we need to get this intersection point, but also we need to remember that the standard cone makes an angle of pi fourths with the z-axis, okay, because that's going to help us with our phi bounds. Well, what we also need is to find our row bound. So let's state what's easy here first, okay? First of all, phi is starting at pi fourths, and then it is cruising down to the y-axis. So that tells me that phi starts at pi fourths and ends at pi halves. We were not restricted to an octant other than above the xy plane, so that tells me that this is a full hemisphere that swirls all the way around the z-axis, so that theta starts at 0 and goes all the way to 2 pi. Now I need to figure out what is going on right here. Oh, actually, no, I'm okay. We're within the sphere, so that should just be 1. This just tells me rho is equal to 1. We are not actually inside of the cone, we're outside of it and in the sphere. So we also know that rho is going from 0 to 1. We'll work on another problem where we have to worry about the intersection, but we're good here. Okay, so these are our bounds. Yay, we got our bounds. Now we need to deal with, oh, you know what? We need to deal with, hold on one second here. Sorry, I was looking at my notes and I was confusing myself, but I have in my notes another way for you to find out phi in case you forget that the standard cone is pi fourths. And I should probably just go over that really quick. So another way to figure out phi. Now remember, we already got phi, just kind of using some logic, but we want an algebraic way as well. So if we have z is equal to the square root of x squared plus y squared, then we can square both sides and have z squared is equal to x squared plus y squared. We stated even in the previous problem that x squared plus y squared can be rewritten as rho squared without the z squared, or in other words, minus z squared. Now, if we bring everything to the left-hand side, that means 2z squared is, minus rho squared is equal to 0. Now, again, I'm going to do that substitution where z is equal to rho cosine phi. So we get 2 rho squared cosine squared of phi minus rho squared is equal to 0. If I factor out a rho squared, I leave behind 2 cosine squared of phi minus 1 is equal to 0. So this is an equation that I would solve. I get rho equals 0, which doesn't actually give me any information that I need. Or we get cosine squared of phi is equal to 1/2, which means cosine of phi would be equal to plus or minus 1 over the square root of 2. And cosine is equal to 1 over the square root of 2 whenever phi is equal to, well, pi fourths or 3 pi fourths. Okay, now we want our cone above the xy plane, so we're going to cross out the 3 pi fourths and go with phi is pi fourths. And that gives us the equation of the cone. Okay, so it's a bit of work to get there, but if you forget, that's how you do it. Okay, moving on. We have the bounds that we need. We know that our integrand is 1, so we can go ahead and calculate the volume. Let's go ahead and do theta on the outside this time. So we'll do 0 to 2 pi. In the middle, we'll do phi. We've got pi fourths to pi halves. And then we have 0 to 1 for rho. Our integrand is 1. We have to remember that dv is rho squared sine of phi. And then d, we're doing this d rho, d phi, d theta. Okay, so let's put that in there. Rho squared sine of phi, d rho, d phi, d theta. All right, so the first piece is going to be our A. The second piece, the middle piece, will be our B. And finally, the last piece will be for C. So for A, we're handling the integral from 0 to 1 of rho squared sine of phi d rho. Sine of phi is just a constant, so I'm worried about the rho squared, which becomes a 1/3 rho cubed sine of phi. Hold on a second. I did something else, and I'm sure if you were watching the video earlier, you're like, wait, no, Jen, it's not 1. It's not 1. This is a sphere with a radius of 2. So this should be going from 0 to 2. I got myself stuck on the last problem. Okay, quick fix. Sorry about that. We're going from 0 to 2. And now when I plug in my 2, I'm going to get 2 cubed, which gives me 8/3 sine of phi. The contribution from 0 is nothing. And so this right here is my integrand for B. All right, so for B, we're doing the middle integral. It's from pi fourths to pi halves of 8/3 sine of phi d phi. The antiderivative of sine of phi is negative cosine, so I get a negative 8/3 cosine of phi from pi fourths to pi halves. I'll hold the minus 8/3 on the outside and evaluate cosine of pi over 2. minus cosine of pi over 4. Cosine of pi over 2 is 0. So this gives me minus 8/3 times a negative root 2 over 2 from the evaluation of cosine of pi fourths. That's great because this simplifies. I get a double negative, and this is going to be 4 square root of 2 over 3. Okay, and then this is my integrand for c. And then finally for c, we have the integral from 0 to 2 pi of 4 square root 2 over 3 times d theta. That just gives us 4 square root 2 over 3 theta, evaluated from 0 to 2 pi. This is going to give me 8 root 2 pi over 3. And that is our final answer for the amount of volume that is contained inside of the hemisphere with radius 2, that is the region below the cone, the standard cone, and above the xy plane. All right, let's see what else we've got. So for the remaining problems, we're supposed to use the coordinate system that seems easiest and most appropriate. And we're not going to evaluate. We are just going to focus on setting these up. I'm not necessarily asking that you set up both ways, but like as you're working through this, start thinking, well, what makes sense? Like, am I naturally thinking cylindrical or am I naturally thinking spherical? Okay. And at this point in the game, you might not naturally be thinking anything, but which one just seems the easiest one to come up with the bounds for the coordinates? Okay. So for this first one, we want to write an iterated integral, which gives the volume of the region E bounded below by z equals the square root of 3x squared plus 3y squared, and above by x squared plus y squared plus z squared is equal to 4. Okay, so this is kind of opposite to what we were just dealing with. So we've got a sphere, and we have a cone. I'm not sure how big that cone is, might be kind of big. Okay. So I've drawn the cone so that it extends beyond the sphere, just so you know that it doesn't stop at the sphere. Okay. We want the volume of the region that is bounded below by the cone. So that means, and then above by the sphere, that means we want the region that is contained fully inside of the sphere and the cone. Okay. Not extending beyond the sphere. All right. So the sphere is like an upper bound. So we could say, let's actually go ahead and fix this then, that we really do want this to be just that part. It's like an ice cream cone, we could say. All right, so we could say that, well, I'm not sure what this angle is that's created with the z-axis in order to determine my phi. I'm kind of seeing that there are two ways for us to handle this, and I'm, funny enough, thinking that cylindrical would actually be the easiest way for us to handle this. Here's why. So number one, I have a z floor, and the z floor is z equals the square root of 3 times x squared plus y squared. We also have a z ceiling, and that is dealt with the upper half of the sphere. So I'd solve for z equals the square root of 4 minus x squared plus y squared. And just looking at those, I'm thinking, oh, okay, well, x squared plus y squared is r squared. So I can get a really easy conversion into cylindrical without having to figure out angles. Like right now, I don't know what phi would describe the cone z equals the square root of 3x squared plus 3y squared. So this is easiest done with cylindrical. What I do need to figure out, though, is what is this circle? Like, what's the equation of this circle? Because that's the circle of values that I need to project on the xy plane to figure out what x and y are doing. Like, in other words, what's that radius and what's the theta? So I need the equation of this circle. To figure out x and y values. To find the equation of that circle, I'm simply going to take the cone and substitute it into the sphere. And so that means I'll need to square it, and I get x squared plus y squared plus, and now instead of z squared, I have 3x squared plus 3y squared is equal to 4. So that means I have a total of 4x squared plus 4y squared is equal to 4. Dividing out the 4, I have a unit circle. Okay, so that is the image that gets projected onto the xy plane. Just a unit circle. And so in polar, I know that r will go from 0 to 1, while theta will go from 0 to 2 pi. And so at this point, I have all my bounds. It wasn't too much work to get them, so I can go ahead and replace everything in a volume integral. So the volume integral, if you recall, is a triple integral over e of 1 dv. But if I'm going to go to cylindrical, then I have my r bounds, my theta bounds, and I've got my z bounds. I'm actually going to do theta last. So theta goes from 0 to 2 pi, r goes from 0 to 1. Z bounds, we're going from the floor. Well, let's recall this is going to be equals the square root of 3r squared, which is going to be the square root of 3 times r for a lower bound. And that upper bound right here is going to equal the square root of 4 minus r squared. So the lower bound is square root 3 times r. The upper bound is the square root of 4 minus r squared. Our integrand is 1. We have to remember that the differential has an extra r in it, and then dz, dr, d theta. That would calculate our volume for us. Okay? All right, the next problem, we're supposed to write an iterated integral which gives the volume of the solid enclosed by z squared equals x squared plus y squared, z equals 1, and z equals 2. Now, the z squared equals x squared plus y squared is a full cone. So to draw a full cone, I draw an x, and I put circles at the top and the bottom. Okay, now I also have the planes z equals 1 and z equals 2. Could call this 1 and this 2. So it looks like what I have here for a shape is just this shape right here. You know what this looks like? A dog bowl. That's it. So we want to find the volume of this region right here. And we know this is a standard cone because it's just z squared equals x squared plus y squared. There are no multipliers on x squared and y squared. So this is, well, for the upper half, it's phi equals pi fourths. That's the angle that's created right here. So that tells me right away that phi is defined between 0 and pi fourths. Because we do have our, or what's it called, our dog bowls going all the way around the z-axis, theta gets to take a full trip around from 0 to 2 pi. Now, we're worried about rho. Not sure what's going on with rho there. Rho is definitely changing, and so we've got to figure out how. Now I'm looking at the z equals 1 and z equals 2, and I want to play with that for a little bit because that's telling me that z is between 1 and 2. Now z in spherical is rho cosine phi, so that means rho cosine phi is between 1 and 2. Now we're trying to find rho. We already have bounds for phi. So it looks like maybe I could go ahead and isolate rho, and I get 1 over cosine of phi is less than or equal to rho is less than or equal to 2 over cosine of phi. And so that means that phi is trapped somewhere between secant of phi, rho is trapped somewhere between secant of phi and 2 secant of phi. Those are our bounds. Okay? So sometimes one of your variables is not going to be bounded by constants. It's going to be bounded by functions. And so you have to play a little bit sometimes to find those, but we got it. So now we can find an integral. The volume would be the integral, triple integral. We have a 1. And let's see, we're in spherical, so we have to remember dv has that extra rho squared sine of phi. And I need to do rho first because rho has phi's in it. So rho had better come before phi. So rho will be the innermost integral, secant of phi. My phi's are getting worse and worse as I go. 2 secant of phi. So we'll do d rho first. Then we can do d phi. And so d phi is going from 0 to pi over 4. And then we can do d theta, and theta goes from 0 to 2 pi. Evaluating this integral would get you what you need. It might be that, let's see, when you evaluate for rho, you're going to end up with some secant squareds, and you have that sign, so don't be afraid to use some trig identities to help you get an integrand that you can actually integrate. Okay, if you want to try this, the answer is 7 pi over 3, just in case you're curious. Okay, all right, next one, C. We're going to let E be the solid enclosed by z equals x squared plus y squared, and z is equal to 9. We want to rewrite the triple integral over E of x dv as an iterated integral. Okay? So here, again, all we're doing is trying to figure out, should we use cylindrical, should we use spherical? Okay, so I'm going to go ahead and draw this. This z is equal to x squared plus y squared. We have to remember that this is a paraboloid. So it just looks like a bowl. And z equals 9 could be its top. So if I draw this on an xyz octant, I could call this 9. Okay? This is a solid. We're going to integrate over this whole thing. It looks like it would probably be easiest to deal with cylindrical with this because trying to come up with a rho on a paraboloid doesn't really make sense because I don't have a radial arm on a paraboloid. It would make things a lot uglier here. So I'm going to go for cylindrical. And for cylindrical, it looks like I have a z floor is the paraboloid, and then I also have a z ceiling, and that is the plane z equals 9. So it looks like I have x squared plus y squared is less than or equal to z is less than or equal to 9. And that can be rewritten as r squared is less than or equal to z, which is less than or equal to 9. Those are going to be my bounds for z. Now, what I need to figure out is for x and y, because that'll allow me to get my r and my theta. This ring across here is the intersection of the plane z equals 9 and the paraboloid. So we're gonna set them equal to each other, right? So we have x squared plus y squared is equal to 9. That's what we project onto the xy plane. Can draw ourselves a circle with radius 3. And so what that tells me is that r is going to go from 0 to 3, and we have a full circle, so theta is going from 0 to 2 pi. All right, now I need to change this integral fully. It's the triple integral over e of x dv. The x, if you recall, x is equal to r cosine theta. Okay, so we have to remember that x is equal to r cosine theta, and we have to remember that dv will be r dz dr d theta. Okay, so rewriting this, the outer integrals for theta, so 0 to 2 pi. The middle integrals for r, so we're going to go from 0 to 3. The inner integral is for z, so it's r squared to 9. My x is r cosine theta. My dv is r dz dr d theta. And then I could just rewrite this one more time because I have r times r, that gives me r squared. So this is 0 to 2 pi, 0 to 3, r squared to 9 of r squared cosine of theta dz dr d theta. Awesome. All right, one more of these where we have to decide which one we want to use. So here we're going to let e be the solid inside both z equals the square root of x squared plus y squared and x squared plus y squared plus z squared equals 1. We're going to write a triple integral of z dv as an iterated integral. Okay, so this is very similar shape to what we had before. Let's go up here in part A, and I used cylindrical then. And I used cylindrical because it was a non-standard cone. But with this one, in part D, z equals x squared plus y, or square root of x squared plus y squared. That's just v is equal to pi fourths. And so I really want to stress you knowing your standard cone in terms of its spherical coordinates. So that makes it a little bit easier. All right, so we've got a sphere, just to confirm that this is the shape I said it was. Here's our sphere. We have a cone. And this is on an axis, the XYZ octant. And we want the solid inside both the cone and the sphere, so we are again dealing with the ice cream cone situation. So everything inside the cone and inside the sphere. Okay, this tells me that phi is starting at the z-axis, which is 0, and going out to pi fourths, which is the cone. This tells me that rho is following the sphere, right? So we've got rho, this is a unit sphere, don't want to make that mistake again. So rho just goes from 0 to 1, and this is a full circle. So theta is going from 0 to 2 pi. All right, that wasn't too bad. Let's see, we've got z, the integrand, so these are our bounds. So for the integrand, we have z is equal to rho cosine of phi, and we have dv is equal to rho squared sine of phi, d rho, d phi, d theta, or something like that. And so then the triple integral over e of z dv will be equal to the integral 0 to 2 pi for theta on the outside. In the middle is phi, so we'll go 0 to pi fourths. In the inner one is rho, so we'll go 0 to 1. The z gets replaced with rho cosine of phi, and the dv gets replaced with rho squared sine of phi, d rho, d phi, d theta. And that does simplify just a bit, 0 to 2 pi, 0 to pi over 4, 0 to 1 of rho cubed cosine of phi, sine of phi, d rho, d phi, d theta. And that's what we would integrate. Okay? All right, so that gives you kind of an idea of like in parts A and B, you see the cylindrical and then you see it in the spherical, and like kind of when you would use one over the other. All right, next example, we just have two more. In the next example, we're evaluating the triple integral over B of e raised to goodness, a horrible expression, x squared plus y squared plus z squared, all raised, again, to the 3/2 power. And B is defined to be, this is called the unit ball. That's why they're calling it B. So x squared plus y squared plus z squared less than or equal to 1. That means the solid unit ball. It's a sphere. And that gives us an easy way to get to our bounds, because for a full sphere, we know that we have theta going from 0 to 2 pi. We know we have phi going from 0 to pi. And it's a unit sphere, so we have rho going from 0 to 1. Now this integrand, that's a little more work, but not a lot. E raised to the x squared plus y squared plus z squared, all of that raised to the 3/2 power, that needs to be converted to spherical. And we know that x squared plus y squared plus z squared is rho squared. So don't you dare start plugging in the separate coordinates for x, y, and z, because you're going to make it so painful for yourself. Just remember, x squared plus y squared plus z squared is rho squared. That makes this a lot easier. So this is e raised to the rho squared, all of that raised to the 3/2 power. The square raised to the 3/2 power, power to a power you multiply. So this is going to be e raised to the rho cubed. And that's not so bad. Okay, and then we need to remember that dv is rho squared sine of phi, and then we can do d rho, d phi, d theta. All right, let's rewrite this. So we have the triple integral over b of e to the x squared plus y squared plus z squared, all raised to the 3/2 power dv, will equal, the outer integral will be theta, so 0 to 2 pi. The middle integral will be phi, so 0 to pi. The inner integral will be rho, so 0 to 1. Our integrand is e to the rho cubed times the differential, rho squared, sine of phi, d rho, d phi, d theta. Okay, now I can deal with the inner part. That'll be a. We've got b, and then we have c. So the inner integral, 0 to 1, of e, I'm going to rewrite this as rho squared e to the rho cubed sine of phi, d rho. So remember, we're not dealing with phi, we're dealing with rho, so we'll handle that. This looks like a u sub. If I let u equal rho cubed, then du will be 3 rho squared d rho. I don't have a 3, so I'll divide. I get 1/3 du is equal to rho squared d rho. So then I'm dealing with the integral of 1/3 e to the u du, which is just 1/3 e to the u. That's not so bad. All right, so this gives me a sine of phi on the outside. I'll just go ahead and deal with that as like a constant, times 1/3 e to the rho cubed from 0 to 1. Well, this just becomes sine of phi times 1/3 e to the 1 minus 1/3 e to the 0. Well, that's just 1/3 e minus 1/3. Or I could rewrite that as, let's rewrite this as equals 1/3 times e minus 1 times sine of phi. And then that is my integrand for b. All right, B, what we have is the integral from 0 to pi of this constant, 1/3 e minus 1 sine of phi d phi. This gives me 1/3 times e minus 1. The antiderivative of sine is negative cosine, so I'll put a negative in here. Cosine of phi from 0 to pi. Okay, so I have my negative 1/3 e minus 1, and then times cosine of pi minus cosine of 0. Cosine of pi is negative 1, and then minus 1, so that's going to give me a negative 2. So I get a negative 2 times a negative 1/3 is a positive 2/3 times e minus 1. All right, this is my integrand for C. So with C, I'm dealing with the integral from 0 to 2 pi of this 2/3 e minus 1 d theta. Well, that's all just a constant. So I have 2/3 e minus 1 theta from 0 to 2 pi. That's just going to give me a 2 pi. So in total, I have 4 pi over 3 times e minus 1. And that is the final answer for that problem. Okay. All right, so for the next one, we're going to use spherical coordinates to find the volume of the solid that lies above the cone and below the sphere. So we're doing another one of those, except this sphere is a little different. We have x squared plus y squared plus z squared is equal to z. So this sphere has been shifted, and I need to complete the square in order to figure out how. So I move everything over. X squared plus y squared plus z squared minus z. I'm going to complete the square, so I have to add something, and that's equal to 0 plus something. Now remember, we take the constant in front of the z term, so we have negative 1, divide it by 2 and square it for a 1/4. So I'm adding a 1/4 to both sides. That means the equation of my sphere is x squared plus y squared plus z minus a half all squared is equal to a 1/4. Okay, so this tells me my center is at 0, 0, 1/2, and the radius is r equals, or rho, sorry, rho equals 1/2. Okay, so I have to draw this. Drawing a sphere is not too bad. What's different about this sphere is it has been shifted up half a unit, and the radius is half a unit. So that means that this sphere has its butt sitting at the origin. And now the cone also has its butt sitting at the origin, and it's a standard cone. It cuts through at pi/4. Okay, we want the volume that is above the cone and below the sphere. Okay, so that is inside the cone. This is the ice cream cone again, except now we have a bigger top on top. We want all that volume, okay? So again, we have a full circle. We're inside the cone and below the sphere, so that gives us information about our bounds. So full circle tells us that theta goes from 0 to 2 pi. Inside cone and below sphere tells me that phi is going to stop at pi/4, so it starts at 0 and goes to pi/4. What we don't know about is rho. Rho's doing some funny stuff here. So rho depends on the sphere. It's not cutting through in the same place that we're used to it cutting through. So what we have here is the sphere equation, and let's leave it in the form x squared plus y squared plus z squared is equal to z. If I convert that to spherical coordinates, it is rho squared equals rho cosine of phi. Moving everything over, I get rho squared minus rho times cosine of phi is 0. Factor out a rho, we have rho minus cosine of phi is equal to 0. This tells me rho equals 0 and rho is equal to cosine of phi. Those are my bounds. This is telling me rho starts at 0 and goes up to cosine of phi. So rho is dependent on the angle phi in order to determine, where we are on the sphere as it sweeps out. Okay, so a volume integral for us, remember the integrand is 1. We have all of our bounds. I'm going to go ahead and set this up with theta on the outside. We are going full circle, so 0 to 2 pi. In the middle, we'll do our phi, so 0 to pi fourths. But then the inside will be for rho. We're going 0 to cosine of phi. And then we have 1 for the integrand. And then the differential is rho squared sine of phi. And this is d rho, d phi, d theta. Okay. I want to show you something here where, the theta, there is no function of theta in here. So I'm going to do something kind of funky here where I notice that theta is not involved, and this is something that is actually legal to do. I'm going to go ahead and break off the 0 to 2 pi, and it'll be a multiplier in the end. And then we'll just focus on the 0 to pi fourths and the 0 to cosine of phi on the inside for rho squared sine of phi d rho d phi. What this allows me to do is handle two antiderivatives at the same time. I'm going to integrate with respect to theta right now. I get just theta evaluated from 0 to 2 pi. I'm still multiplying, okay? And then times the integral from 0 to pi fourths. And now I'm going to go ahead and integrate with respect to rho. I get 1/3 rho cubed sine of phi evaluated from 0 to cosine of phi. And then I would still have a d phi on the outside here. Okay, the theta from 0 to 2 pi just gives me 2 pi. And we're used to that. We've seen this so many times that the contribution from d theta just gives us 2 pi. Then we have the integral from 0 to pi fourths. And now we're going to evaluate this 1/3 rho cubed at cosine phi. So it gives me 1/3 cosine cubed of phi sine of phi. The contribution from 0 is nothing, so I'm done now at this point. And now we have something we can integrate with respect to phi. We have a u sub, and the u sub says that u should be cosine of phi because the sine is a single power, so du will be minus sine of phi d phi. But then we don't have a negative, so we'll move that negative over, and negative du will replace sine of phi d phi. So if I handle just that, I'm looking at the negative integral of u cubed du, which gives me a negative 1/4 u to the fourth, and that's it. All right, so let's go ahead and take care of this. I still have my 2 pi, and then I get a negative 1/4 cosine to the fourth of phi from 0 to pi over 4. That negative 1/4 can actually come out and join the 2 pi. We'll get a negative pi over 2, and then I'm looking at cosine to the fourth of pi over 4 minus cosine to the fourth of 0. Cosine at pi over 4 is root 2 over 2, so I get this is negative pi halves times root 2 over 2 to the fourth minus cosine of 0 is 1, and 1 to the fourth is just 1. All right, that root 2 over 2 to the fourth power ends up giving me 4 over 16. So I have negative pi halves 4 over 16 minus 1. That's going to give me a negative 3/4. So negative pi halves times a negative 3/4 is equal to a positive 3 pi over 8. think I lost something out here. I did. Hang on. I lost my 1/3. I should put this out here. 2 pi over 3. Then if I join up the 2 pi over 3 with the 4, this will be a pi over 6. This will be a pi over 6. This will be a pi over 6. Still a pi over 6. And finally, we end up with a 3 pi over 24, which simplifies to pi over 8. Phew, okay. All right, that is it for 15.8. It's kind of a long section. I did a lot of examples so that you see a lot of different situations and how to handle them and how to come up with those bounds. And spherical is very new, while cylindrical was more of a play on polar. If you do have any questions, feel free to reach out. I'm happy to help.